Okay. I knew that for week one, that we were going to be in a bit of a bind since the week starts on Wednesday and we don't get to have our lecture until Tuesday. So, because of that, I've decided to go ahead and record a lecture over chapters one and two to be available to you guys so that you can watch it, um, get prepared to be able to work some of the homework for chapters one and two and be ready for the lecture when it does come around. And then at that point, we can also discuss chapters three and four. So here we go. Chapter one is an introduction to measurement. How are measurements done? In section 1.1, you're going to be basically learning the how you measure things, including lengths, identifying the base quantities in the SI system, and to name the most frequently used prefixes for those units, and then change units for length, area, and volume by using the chain link conversions. And then we're going to go over the definition of a meter and how that's changed and what it is now. So basically, a unit for measurement, is the unique name assigned to a measure of a quantity, be it mass, time, length, pressure, what have you. It's basically we need to have some sort of defined um, quantity that we can talk about, because if we can't define a particular uh, quantity, then we could be discussing different things, but we can't come to a common sense of measurement. And so that's what this is all about. It's a standard. It's something that we can discuss and we know what it is that we're talking about. So, for example, a 1.0 meters is going to be the distance traveled by light in a vacuum over a certain fraction of a second. That's how it's defined. That is the standard. That's what we're going to be discussing. You're going to have many different physical quantities. Not everything is independent. Um, your base quantities, you're going to have seven. They're going to be such things as length and time, and uh, three are going to be needed for mechanics: length, time, and mass. And you've got a certain standard to which all of them are assigned, and they are going to be used to define other physical quantities, more complex notions as we go along. You need to have these base standards be accessible so that you can take a measurement and that they don't vary, so that we can do measurements at different times and still be able to discuss the same thing. So, the International System of Units, or SI units. For length, we're going to be looking at meters. For time, we're going to be looking at seconds. And for mass, it's going to be kilograms. So we're going to have many derived units that use those base units. So a joule is work energy. It's going to be defined as 1 kilogram meter squared over second squared. You're going to have a watt, which is a definition of power, and that's going to be a joule per second. Or if you take the definition there on the right side for a joule, it's going to be 1 kilogram meter squared per seconds cubed. Scientific notation. Many times in physics, we're going to have numbers that are written that are going to be very, very large or very, very small. And what scientific notation attempts to do is to take that information and try to condense it into a number using a number between 0 and 9, or 0 and 10, I suppose. And it's going to be multiplied by a certain power of 10. And then you're going to have a unit at the end of it, which will give you a shorthand way of being able to discuss something. So, for instance, you've got something here. You've got, let's see, hundreds, thousands, millions. So you've got 3,560,000,000 meters. It's a pretty long number if you write it all out. Well, if you condense it down into scientific notation, it looks like this. You can recognize the 3, the 5, and the 6. They're all from this part over here. But where did this 10 to the 9th come from? That came from the fact that normally your decimal point is going to be right here in between this and wherever your unit is. Or it may already be written down in the number if they choose to write it that way. This exponent comes from where this decimal has to move in order to be positioned right there, or right here, between the last non-zero digit that you have over here and then whatever remains over here. So if we move this decimal point over here, that would be 3 spaces. If we move it here, that would be another 3. And if we finally get it here to where we have the last non-zero digit right here, we will have moved it 9 spaces over. The other way to look at that is that if we take 3.56 and multiply it by 10 9 times, it would be the same value. These numbers are the same. So here we have 3.56 times 10 to the 9th meters. That's the same as this. If you take that decimal point and you move it over this way, you move it 9 times to the left. And what that means is that essentially you're taking 3.56 and multiplying it by 10 9 times over, and that produces this value. For here, we're going to move the decimal point all right, but we're going to move it in the opposite direction. We're going to move it to the right because this number is very, very small. So as we do that, we move the decimal point 1, 2, 3, 4, 5, 6, 7. This is our first non-zero digit here. So it's going to be 4.92 because that's what follows here. And that's going to be multiplied by 10 to the minus 7th. It is to the minus 7th because we are moving the decimal point to the right in order to be able to establish this number. So we move it 7 times over. 1, 6, 7. So we have 4.92 times 10 to the minus 7th seconds. So now, the next part is a conversion factor. And this is going to be a ratio of units that is equal to 1. The reason these are important is we want to change from one unit to another. So, for example, if we've got 2 minutes, 2 minutes multiplied by 1 is still going to be 2 minutes. This 1, however, is going to change into this particular conversion factor. This particular conversion factor is 60 seconds over 1 minute. Well, how do we get away with that? Well, 60 seconds divided by 1 minute, this would be the same as 60 seconds divided by 60 seconds, or 1 minute divided by 1 minute. It's the same quantity. So that divided by itself is always going to produce 1. The advantage that this gives us is that if we write it with 60 seconds divided by 1 minute, if we multiply that by 2 minutes, the minutes here cancel, and that leaves us with seconds. And if we take the 60 and multiply it by the 2, that gives us 120 seconds. This is a way of changing from minutes to seconds, meters to millimeters, what have you. If we're going to change a unit from one length into the next, and we know how they are equivalent to each other, this is how we go about doing it. And these units obey the same algebraic rules as variables and numbers. Okay, so the needs for accuracy in science have been driving changes in the standard for units. In the past, the meter has been defined all kinds of ways. 1/10,000,000th of the distance from the North Pole to the equator. Not quite sure how useful that is, but there we are. We've got a platinum iridium standard meter bar kept in France, like you do. And then we have another way of measuring a meter of 1,650,763.73 wavelengths of the emission line of KR86. But today, we're going to define the meter as the length of the path traveled by light in a vacuum during the time interval of 1/299,792,458 of a second. So In each transition, the new distance was chosen so that the approximate length of 1 meter was preserved. I'm sure that they differ to some degree, but this is what we finally settled on. I suppose because this could be produced all over the globe and you would still end up with the same length. That's the theory. So here's some more definitions regarding significant figures. Generally, you're going to round to the least number of significant figures of the given data. So 25 times 18 is going to be 2 significant figures because you've got 2 non-zero digits here, 2 non-zero digits here. So if you multiply a number with 2 significant figures and then another number with 5 significant figures, your overall significant figures is still going to be 2. So round up for 5 plus. So if you're looking at 5 plus 13.5, that would round up to 14, but 13.4 would round down to 13. So in other words, if your digit here is going to be 5 or greater, then you're going to round up. If your last digit here is going to be 4 or less, then you round down. Significant figures are not the same thing as decimal places. So you may have 5 decimal places here, but you've only got 3 significant figures because these are the non-zero figures right here. Trailing zeros are not significant. In other words, if you have trailing zeros after that, basically what you're implying is you've got a level of precision there that you may or may not actually have. So we don't consider that to be significant. So here, in other words, 3000 may have 4 significant figures, but usually 3000 will only have 1 significant figure. In other words, you've got a 3000 there. You have to have these 3 zeros there in order to be able to tell you that's 3000. Otherwise, it would just be 3. But technically, you've only got 1 non-zero digit here, and so that's going to have 1 significant figure. That's really how that should have been, but it wasn't. When in doubt, use scientific notation. Changing into a form like this, that's very clear as far as the number of significant figures that you have. So here you've got some examples that you can work through regarding chain link conversions. I'm going to leave that to you. I trust that you can do that. And if you can't, if you have some difficulties, please do let me know. Section 1.2. We're going to change units for time using chain link conversions and various measures of time, such as for motion or measured on different clocks. So, time. Any standard of time needs to be able to answer when did a thing happen and how long did it last. So, times follow the same conversion process as lengths. Standards of time in the past have been measured with rotation of the Earth. Obviously, you see the day change to night, and so on and so forth. Quartz vibrations, you also have atomic clocks measured with cesium, with time signals sent out by radio so others can calibrate the clocks. 1 second is the time taken by 9,192,631,770 oscillations of the light of a specified wavelength emitted by a cesium-133 atom. I'll bet you didn't know that. So the variation in the length of a day is measured by an atomic clock. The vertical scale here amounts to only 3 milliseconds. And this shows the precision of atomic clocks and the relative imprecision of the Earth's rotation. It's affected by tides, winds, and so on and so forth. And mass. We're going to change units for mass using the same chain link conversions and relative density to mass and volume, where the mass is uniformly distributed. So a standard kilogram is a cylinder of platinum and iridium stored in France. Why in France? Well, why not? We've got accurate copies that have been sent around the world. Other masses can be measured by comparing them against these copies. An atomic mass unit is a second mass standard. And the reason we have that is just an atomic mass unit is very, very small. Kilogram is very, very large by comparison. So this is going to be a second standard. An atomic mass unit is going to be one atom of carbon-12, and that is going to be assigned a mass of 12 units, 12 atomic mass units. It's going to be used for measuring masses of atoms and molecules, again, very, very small. And you can see the conversion factor there. One atomic mass unit is equal to 1.66 and change times 10 to the minus 27 kilograms. And then you can see the plus or minus factor there of, the range of kilograms that could be measured in. And if you're going to do the same conversion process for lengths and times, masses will follow that same convention. So, mass per unit volume is called density. In other words, if you have a mass and if you divide it by how much volume it takes up, boom, you've got your density. You can see the examples there where you can take that formula and you can use it algebraically. You can turn it around, solve it for volume, which would be mass over density, or you can solve it for m, which is going to be the density times the volume. So you can see how the relationships are defined to their base quantities, what their standards are, and where are those standards coming from. The International Systems of Units. That is an attempt for us, for scientists, and well, hopefully the general public, to be able to communicate with each other as far as what these units mean. The other things that we've done is we've done chain link conversions in this course. We've also, or this chapter, we've also written conversion factors as unity, one, taking a factor, multiplying it by one, or that's the same thing as having the same thing on top and bottom. And then we've also found out here that the length of a meter is defined by the distance that traveled by light in a vacuum in a specified time interval. Time, the second, is defined in terms of oscillations of light emitted by a cesium-133 source. And atomic clocks are used as the time standard. For mass, kilogram is defined in terms of a platinum iridium standard mass, and atomic scale masses are measured in atomic mass units, defined as the mass of a carbon-12 atom. Again, here's your equation for density. Okay, that will be chapter 1. I'll do another video here regarding chapter 2 in just a second.